Assalamualaikum. Hi everyone. So, this is the fourth video for chapter 1 reaction kinetics for the subtopic 1.1. So, let's take a look on what we will see today. So, at the end of this lesson, you should be able to determine the order of reaction involving single reactant using the half-life method and also the linear graph method. So, in the previous video, we already talked about the methods to determine order of reaction. We have three methods, which is the initial rate method, half-life method, and the linear graph method. So we already discussed about the initial rate method. So for today, we're going to focus on the half-life method and linear graph method. So let's start with the half-life method. So what is the half-life method? For the half-life method, the order of reaction is determined by analyzing the half-life from the graph of concentration against time. So, for this video, please take the table that I give you before and focus on all the graph inside that table. We're going to look on each and every one of the graph and how to use that graph to determine the order of reaction. So, like I mentioned just now, for the half-life method, the graph that we are going to focus are the graph of concentration against time. Okay, so from this graph, when we plot a graph based on the data that we have, we can determine either our rate of reaction, the order of reaction is either zero order, first order, or second order. Now, plotting graph using the half-life method. So what are the steps to plot the graph? So here are the steps. So the first one, to determine the order of reaction by using this method, we need to plot a concentration versus time. So here, when it says plot, you need to plot your graph on a graph paper using an appropriate scale. Then determine the first half-life and the second half-life from the graph. So this one must be shown clearly in the graph, and then determine the order of reaction. How do we determine the order of reaction? By analyzing the first and the second half-life. So here, if you have the first half-life is bigger than the second half-life, okay, this is show that we have a zero order reaction. If the first half-life is equal to the second half-life, we have a first order reaction, and if the first half-life is smaller than the second half-life, we have a second order reaction. So what do I mean by this? So now let's take a look on a few general graphs. Now let's start with the zero order graph. So for zero order graph, we plot a graph of initial concentration against time. Okay, so I just give you a general graph without any data. So this will be the graph that you will get for concentration against time. So how do we incorporate the half-life method for this to find the order of reaction? Okay, so like I mentioned before, we will analyze it by looking at the first half-life and the second half-life. So the first half-life, it will start here from the initial concentration. So I put it as E0. Okay, so when the initial concentration undergoes the first half-life, the concentration will become half. So we will get here the concentration A0 to the power of 2. So what you will do now here is find the half-life. Okay, how long does it take for the concentration to become half? We need to label the first half-life here. how are we going to label that? So usually what you will do is you will label here half-life. Okay, so this is not the way of labeling the half-life for this method. So the way to label is you do it like this. So the whole thing over here you will label as the first half-life. Okay, so T half 1 like that. Okay, and then the second one, the second half-life. The second half-life will be half from this concentration. So half from this one will be initial concentration over 4, quarter of it. Okay, so let's label that. Okay, so I have my second half-life here based on this concentration, meaning this is my initial concentration for the second half-life. So label the half-life, so I label it here. It's from here to here. So T half second, like that. Okay. So as you can see here, the half-life, the time taken for the concentration to become half as the reaction proceeds will become shorter. Okay, so for us to show that this graph is actually for zero order reaction, you need to know how to write down the information. So you need to have what is the value of the first half-life here, and then what is the value of the second half-life. So the value first half-life is here to here. Okay, so put the value. And then the second half-life from here to here. So put the value. Next, you will state here, so make a conclusion as from what you can see. So from the graph, you see that the first half-life is bigger than the second half-life. So put it down here. Okay. Or sometimes it can be shown like this. So you put or. So where we have the first half-life, here is the first half-life, is actually twice the number of the second half-life, the value of the second half-life. So 2 times the second half-life. Okay, because when you look at the value, for us to say that it is a zero order reaction, the first half-life must be at least twice the value of the second half-life. Okay, what do I mean by this? So if let's say my first half-life is 5 seconds. Okay, and then I have the second half-life, half-life 1. Okay, and then I have the second half-life only as like 4 seconds. Okay, T half second. So for this one, we do not consider it as a zero order reaction. So it must be at least less than that. Meaning, if let's say my first half-life is 5 seconds, T half 1, and my second half-life is 2.5 seconds, T half 2. So if you look here, the second half-life is smaller than the first half-life, and the value of the first half-life is twice the value of the second half-life. So only with information like this, we consider the graph to give us a zero order reaction. So you will need to make a statement, okay, that to conclude, so the reaction is zero order with respect to the concentration of the reactant. So state your reactant. State specifically what is the reactant. And then you will say, so when concentration A0, so what's the value? The T half will equals to what value here? Okay, because as you change the concentration, so let's say when you put the concentration A0 to the power over 2, the T half will differ. Okay, so that's why you need to mention specifically the half-life is for what initial concentration. So if this the first half-life is for the initial concentration here, the second half-life is actually for here the concentration over 2. Okay, so mention specifically. So now let's talk about the first order reaction. So for the first order reaction, when you plot the graph of concentration against time, you will get a curved graph like this. Okay, so how do we analyze that? From this graph, we will get a first order reaction. So the same thing that we did for the zero order reaction. So we look on the initial concentration to find the first half-life. So this will be our first half-life. So like we did just now, label this, okay, as T half 1, and then find the second half-life by halving this concentration. So when we halve this concentration, you will get the concentration as A0 over 4. Okay, so before I proceed, the value that I put here is a general value. So if let's say on your graph that you have scale over here, for instance, you start with 60. The concentration is 60. So the next one will be 30. So the next half-life will be 15. Half the concentration. Okay, so I just show you the general one. Okay, so let me proceed. So this will be the first half-life. So let's look on the second half-life. So this is your second half-life. So let's label this. Okay, here. This time it's your second half-life, T half 2. Okay, so from here what you can see here is the first half-life is equal to the second half-life. Okay, remember your exercise, the one that I gave you on the second part of our tutorial, where I said that for first order reaction, the first half-life is equal to the second half-life. Why do I say it like that? Because it's actually from the graph. Okay, for first order reaction, the half-lives are the same. The first one equals to the second one, and then the second one also equals to the third one. The half-life is constant because if you look back at the half-life equation, our half-life is T half equals to ln 2 over K. So clearly it is stated here that the half-life is not affected by the concentration of the reactant, by the initial concentration of the reactants. So that's why the half-life is the same. So to say that this graph is a first order reaction, you must write down, so the first half-life is equal to the second half-life. Okay, and then say that the reaction is first order with respect to the concentration of A, and depends on what's your reactant. Okay, now, so if the question asks you, what is the value of half-life? Okay, so since the value of half-life here is the same, you can choose any value because it will give you the same answer. Okay, and then before I forget, here you need to mention what is the value of the half-life for this statement to be valid. Okay, you need to show it clearly on the graph. What's the value here? Okay, now, so let's say I take the initial concentration as this one, and the initial concentration is 60. Okay, so to write down the half-life value, so at 60, at concentration A equals to 60 molar, the half-life equals to, okay, so write down the value of the half-life. So for the second order reaction, when you plot the graph of concentration against time, you will also get a curved graph like this. So that's why it is important for us to distinguish between the first order and the second order by recognizing, by analyzing the half-life. Okay, so the same thing, we will take two half-life here. So we will start from here, so our A0, okay, and then next one, so for the first half-life, it will become A0 over 2. So for the second half-life, it's from this concentration. So we will get here A0 over 4. Okay, so let's analyze the half-life. Okay, so let's label this. So I already plotted for the first half-life is here, and the second half-life is here. Okay, so label T12. So make sure you write down what's the value, and then T12. What's the value? So from here, you can see that the first half-life is actually smaller than the second half-life. So you will write it down as a conclusion. So where the T12 is actually smaller than T12. So the condition for this one, okay, for it to be a second order, okay, the value of the second value of the second half-life, okay, so since the second half-life is bigger, the value need to be at least twice the value of the first half-life. Then we can consider it as a second order reaction. Okay, so you will put the conclusion here after you write this part. Okay, next, the conclusion. So the reaction is second order with respect. Okay, so reaction is second order with respect to the concentration of A. Okay, so like before, if the question asks what is the value of half-life, so since here we have two different half-life, so choose any one of the half-life but write with the correct initial concentration. So let's say I want to use this one, the second half-life here. So the second half-life, let's say I put it as the value of X. So this half-life belongs to this concentration. So let me put the concentration, let's say, as 5 molar. Okay, so you will write down, so when the concentration of A
equals to 5 molar, the half-life equals to X second. So it will be like that. So if you choose this one, so let's say you choose the initial concentration here, that will give you the first half-life, Y. So let's say the first, it is 10. So when concentration of A equals to 10 molar, the half-life equals to Y second. So you need to write down only one. So choose which one do you want. Okay. So now let's look at example.
So example, from the following data, determine the order of reaction, but the half-life and the rate constant. So for this one, I want you to use the half-life method, meaning for this one, to use the half-life method, you need to plot concentration of C2H5I against time. Okay, so that will be the graph that you will plot. So I want you to plot it on a graph paper. Okay, so now let's look on what will happen. So there are three things that the question asks for you to find. First, the order of reaction. Okay, this is the first one. Okay, second, the question asks for half-life. And the third one, the question asks for the value of the rate constant. Okay, so for this one, first you will start with plotting the graph. So make sure you use a graph paper to plot this. Okay, so your graph, you need to make sure that you have the title here. Okay, and then the axis with the correct unit. Okay, so plot your graph and then find the first half-life, label the first half-life, and then label the second half-life. Okay, so put it here, the first half-life is equal to the second half-life. So what we don't have here is the value of the half-life. Okay, so please put what is the value of the half-life. Okay, and then you can determine here. Oh, it's actually here. So 70 minutes. So the first half-life equals to second half-life. So it is a first order reaction. Okay, so from here, so the first half-life equals to second half-life. Thus, this is a first order reaction. So settle for the first part. Okay, the second part, the question asks for the value of the T-half. So the value of the T-half is 70 minutes from the graph. So if you already plot a concentration against time graph, so the value of half-life must be taken from the graph. It must be from the graph. Okay, even though you can calculate this value, but you need to take it from the graph here because it's already here. So just take the value. Okay, so that will be the second question. So this is the first one. This is the second one. And then the third one. The question asks to find the value of the rate constant. So for the value of rate constant, since we know this is a first order reaction, so you will use the equation for the half-life for first order reaction, which is T half equals to ln 2 over K. So substitute the value that you already have. The T half is 70 minutes. Okay, and then rearrange until you get the answer. Okay, even though I already put it everything here, okay, in this video, so I still want you to draw the graph as a practice on a graph paper. So just now we have finished discussing to determine the order of reaction by using the half-life method. So right now, let's look on how to determine the order of reaction by using the linear graph method. So the linear graph method, how do we use this method to determine our order of reaction? You need to plot a graph by using the integrated rate law, and the graph that gives us the linear graph will show the reaction order. So for plotting the graph using the linear graph method, this method is done by trial and error. So what does it mean by this? If you obtain a straight line when you plot concentration of reactant versus time, the reaction in zero order with respect to the reactant. But if you plot a graph of concentration of reactant against time, the reaction is first order with respect to that reactant. And if you plot a graph of 1 over reactant against time, you will get a second order reaction. Okay, why this certain graph give you a certain order of reaction? So like I mentioned before, it is because of the graph that we plot from the integrated rate law.
So this is our integrated rate law. So usually from the question will only give you the value of concentration and also time. Okay, so since it's a linear graph method, our target here is to get a linear graph. Once we get a linear graph, then we know that is the order of reaction. So for each order of reaction here, you will need to plot a different graph to determine will you get a linear graph or not. So what set of data do you need? So you need to rearrange everything by using following this equation: y equals to mx plus c. So this is the equation for your linear graph. So rearrange what you since we have a naught, a, and kt over here. So how do we rearrange this? Okay, so it will be like this. So for the zero order reaction, okay, the graph that you need to plot, our y will be A. So it will be concentration of A equals to minus KT plus concentration of A0. Meaning here, the graph that you will plot to get, if it's a zero order reaction, once you plot concentration, if you plot concentration of A against time, you will get a linear graph. Next, for first order reaction, so this is the first order reaction. The one that I give you is either this one, ln A0 minus ln A, or it can also be written like this, A0 over concentration of A, meaning here A at certain time. Okay, but for the sake for finding the data to plot the graph, we will use this one. Okay, so rearrange the equation as well. Our y-axis will be ln A over here. So it will be ln A equals to negative KT plus ln A0. Okay, meaning, so let me put here the data. Okay, the graph for graph. So for first order reaction, what kind of graph will you plot? So you will plot ln A against time. So if you plot ln A against time, you get a straight line graph, a linear graph, meaning the reaction is first order reaction. And then lastly, for the second order reaction, so this is the integrated rate law for the second order reaction. So same goes here, rearrange your equation. So your y-axis will be 1 over A, so KT plus 1 over A0. Okay, so from here, the graph that you need to plot is 1 over A against time. So when you plot the graph of 1 over A against time, if you get a linear graph, meaning it's a second order reaction. Okay, so what do I mean by all of this? So let's take a look on one example.
So let's say I have this set of data. So actually, the question gives me time and concentration of N2O5 only. So for me to know either it is a first order, second order, or zero order reaction, I need to have 3 sets of data, and then I need to try one by one which one will give me a linear graph. So you need to set the table here. You need to have all the data, because as you know, for the zero order reaction, it's concentration against time. For the first order reaction, ln concentration against time, and for the second order reaction is 1 over concentration against time. So plot it one by one. Okay, so this one here, okay, so this is for the zero order. Okay, zero order graph. Sorry, it's not a zero order graph. Okay, it's concentration of A against time for zero order reaction. So if you look here, we did not get any straight line graph, not a linear graph. It's a curved graph, meaning it's not a zero order reaction. Okay, not a zero order reaction. Okay, the next one is this one. I plot ln concentration against time. So ln A against time. So from here, so this is for our first order reaction. So I just put here first order. Okay, from this one, when we plot ln A against time, sorry, it's not ln A. You need to make sure that this is the N2O5. Okay, N2O5. So when we plot the concentration against time, what we get is a linear graph. So most probably, this is a first order reaction, but to make full sure that it is a first order reaction, so since we already have the data here, so let's plot the ln, 1 over N2O5 against time. So this is for the second order. So when we plot 1 over concentration against time, we get a curved graph. So from here, we can conclude that since it's a linear method, a linear graph method, we want to find a linear graph to determine the order of reaction. So from the 3 graph here, it is concluded that the first order reaction, which is the graph of ln A versus T, this is our order of reaction. So the reaction is first order with respect to N2O5. So this is how you do. So if the question asks you to find the order of reaction by using a linear graph method, so you need to know which one is the correct one. So like I mentioned before, it's a trial and error. Okay. So maybe at this time, at this moment, you already panic. Madam, in exam, nak kena draw 3 graph ke madam to determine the order of reaction? Okay, so for this one, there is some tips on how to determine which graph do we need. Okay, so I will make a separate video for that one, and that will be all for this video. Okay, we have come to the end of our lesson. So, thank you, and I will meet you again in the next video. Bye!